Hello everyone, welcome to our new video on Euclid Mathematics. In my today's video, I will explain Uniform Convergence test, which we started a lecture series on real analysis. For more videos like Weierstrass test, Dirichlet test, Yeoman test for Uniformly Convergence test, you can check it in my playlist. More videos are there. I solved more and more examples in order to understand this concept more better. Okay, so in my today's video, I'm going to explain ABEL'S test for uniformly convergent series. Okay, so if we wanted to check whether series of functions uniformly convergent or not, then we apply here ABEL'S test. Similarly, we use Weierstrass test and Dirichlet test also. So you can apply any one of them, but I feel that ABEL'S test is also one of the good tests that we can get the uniformly convergence easily. Okay, so let's get started our today's lecture with ABEL'S test for uniformly convergent of a series of function. Okay, so ABEL'S test it says that if we write that our function fnx as a series of unx into vnx, similarly like a Dirichlet test, nothing is different but some of the property extra here. Okay, so it is a series unx into vnx. It is uniformly convergent. When it is uniformly convergent, that we have first property that one of them has to be a uniformly convergent in a closed interval AB. Okay, so we have to check uniformly convergence for one of the value. Okay, second property, it says that remaining value, okay, if one is uniformly convergent, then remaining here vnx, okay, it is monotonically decreasing. That means it goes to smaller and smaller. And third property, it is uniformly bounded on closed interval AB. I explained in my previous lecture what is meant by uniformly boundedness. Okay, that means our given function v of x, sequence of function v of x, it is bounded by some constant values. Okay, so we say that sequence of function vnx is uniformly bounded on closed interval AB. Okay, that means it inside that interval AB. Okay, then we say that series fnx, which is the series unx into vnx, is uniformly convergent. Okay, so it's quite easy to understand, a very easy test that we can easily apply in our examples. Okay, so you can understand it more better once we solve some of the examples. Okay, now let's get started with some examples here. So I took it here one example that it says that we have series fnx, which is a minus 1 raised to n minus 1 upon n into x raised to n. Okay, and you can see that this interval is more important. Okay, because everything depend on that interval. If that interval change, that uniform convergence state change. Okay, so you can see x is here on that interval. So we have to decide which one of the vnx and which one of the unx. Okay, so you have to find out first which is a possible to check uniformly convergent. Okay, so you can see that unx, if you consider unx minus 1 raised to n minus 1 upon n, it is easier to check uniform convergence than x raised to n. Okay, because we know that Leibniz test for alternating convergent series, okay, that says that if we have alternating series like minus 1 raised to n minus 1, it is alternating series which gives value plus 1 minus 1 plus 1 minus 1, like this way. Okay, this is the alternating series. Okay, so if we have such a type of alternating series, and when we apply limit n tends to infinity to that series gives us value 0. So what it is possible, can we say that if n tends to infinity, that series gives value 0? Yes, exactly, because this values interval. Okay, and when we apply limit n tends to infinity, that unx, I consider unx, we know that n tends to infinity, 1 upon infinity, it goes to 0. Okay, so this one is goes to 0 because minus 1 raised to n minus 1, if we take the power of 1 or minus 1, it does not affect on our function. Okay, so here denominator n, here when we apply limit n tends to infinity, unx goes to 0. Okay, so that means by using Leibniz test, we can say that unx is a uniformly convergent, and vnx is given x raised to n, but x belongs to from where? Close 0, open close 0, 1. Okay, and when n goes to infinity in under close 0, 1, that terms goes to approaches to 0 and closer to 0. Okay, so when it approaches to closer to 0, then we say that it goes to smaller and smaller. Okay, so then we can say that vnx is uniformly bounded and monotonically decreasing. Okay, so it is uniformly bounded here and bounded, which is by we have close into 0, 1. Okay, and now next task is here that the other series need to be uniformly convergent. Okay, so you can see that minus 1 raised to n minus 1 upon n is a convergent because of that Leibniz test for alternating convergence series. Okay, and Leibniz test it says that unx, that function unx, when we apply limit n tends to infinity, it goes to 0, and there is sequence of partial sum like u1 minus u2 plus u3, it is goes to smaller and smaller. Okay, that means if un is bigger, then u2 is smaller, then u3 is smaller than u2, then it is goes to smaller and smaller. Okay, so this is the term that goes to smaller and smaller. So by using Leibniz test, we can say that unx is a convergent. Okay, so if it is uniformly convergent, then we can say that our whole sequence of function fnx, which is the minus 1 raised to n upon n into x raised to n, is uniformly convergent on closed 0, 1. Okay, So this one is the example on ABEL test. I hope so you all have understood. Now let's see some of the property which we need here to solve sequence of function, whether it is convergent or not. Okay, now let's get started to properties. So here first property, it says that if series f and x is uniformly convergent, okay, and converges to fx, okay, so f and x is uniformly convergent and it converges to fx, okay, then our first property, it says that if each term of a continuous function, okay, if we expand that f and x, like f1x, f2x, f3x and so on, okay, that means f1x is a continuous function, f2 is a continuous function, f3 is continuous function, and when we take sum of all continuous function, then we say that sum of a function of fx is also continuous, okay. So if we take the sum for all these f and x, we get the fx which is also continuous function, okay. Now second property, it says that if limit x tends to a series f and x, which is equal to series limit n tends to infinity f and x, which is equal to limit x tends to a fx, okay. Limit and series has replaced here only, okay. If these properties need to be followed, okay. Now here next property, it says that series f and x is converges uniformly to fx, okay. F and x converges uniformly to fx and f and x is a differentiable for each n belongs to n, okay. So that means it has to be a derivable, okay. Its derivative has to exist for all natural number, okay. It is from n, and series fn dash x, okay, nth term, okay. So nth term is here and its differentiation converges uniformly to gx, okay. Then we say that fn dash of x and which is converges to gx, both are equal, okay. So these are the some of the properties which are easier that we can understand it easily. I hope so you all have understood that definition of ABEL'S test, which is the one of the powerful test to check whether series of function is uniformly convergent or not, and some of the property we saw it here and one examples, okay. I hope so you all have understood my today's lecture for uniform convergence, okay. So thank you everyone, thank you for my today's lecture.